Okay, so welcome to today's lecture in deep learning and neural networks. I hope you're still a bit recalling what we did 2 weeks ago. We started with looking into how networks are trained. So after we did the architecture, we now shifted to the training, and we first looked into the general framework of how things are optimized and what are the standard things. Today we want to go to the next step. I mean, the name is deep learning, and if we're talking about state-of-the-art neural networks, they are typically very deep, meaning we have a lot of different layers. And this makes learning more difficult. And so we will get a bit an overview of some techniques, how to address that, how we can build larger models, which are typically more powerful because we have more parameters to adapt, but that also makes the training more difficult, and we'll want to look at some of the techniques there. So what we'll do is mainly look into 4 parts, where the first 2 are the larger ones. So first, we already introduced the problem of overfitting last time, and today we want to look at 3 techniques a bit to address that. Mainly regularization and dropout, which is like somehow standard in current networks, but we'll see how that works. And then for predicting categories, often what is called as label smoothing is used. So we'll also want to look at label smoothing. And then we'll look a bit more into gradient normalizations and how we can better work with gradients. There we look at 2, batch norm and layer norm, and then also in what is called residual connections, which is similar to have in generally a better flow of the gradients, that it's more easy to learn that. And you'll a bit there in that place also be remembered that what we covered in RNNs, because there we have a similar problem. This time it's just not across the sequence, that the sequence gets long, so the gradient flow is difficult, but we can also have it across the height, because if we're now thinking about that, we have networks with 100 layers, also these has to flow through all the network. Then we'll briefly talk about initialization, and at the end of today, look into what are mixture of experts models, which are trying to more separate the network and have dedicated networks there. But yeah, let's start with the motivation. So where are we? So if you look at how networks are developed, just to recall a bit where we are, we're not really, what you normally have to do first is do your data collection. We haven't really covered that much here because that's more domain dependent. If you're doing speech models, you have to look how to collect speech. If you do text, how to collect text. And if you do vision, how to collect vision. But therefore, this is not covered that much in this lecture. Then we had all the time, like several lectures about the architecture. And what we'll currently add is a training, how to make the training more efficient. And 2 things we looked there at the last time. The one thing is the general setup of the training. If you remember, we wanted to find the optimal parameters, meaning that we want to minimize the loss function here, which is the loss of the whole network. We're generating the output of the network here and comparing it to the reference in the image that is here. So we're comparing the green or purple output to the red reference, and then we're backpropagating the error that we're doing. We are looking with respect to the gradient, storing our derivation, and using that then for gradient descent. So what we have to do for the gradient calculation is always this forward pass, calculating the loss, and then doing the backward propagation. We also looked at the algorithm of how to do that, where we're doing typically the mini batch array. We're getting some samples. We're going over the samples, doing calculating of this gradient that we saw there before, and then we're applying an update. And while the initial idea of the update was quite straightforward, we're just going in the opposite direction of the gradient. we saw that we have to use some more heuristics, and then we came up with later the Adam algorithms or so. So you could now think, yeah, sounds interesting, sounds good. We have done all of that. So what are the open challenges? And one main thing we are seeing when we're looking at current neural networks is that they get really, really, really huge. And that is somehow a very nice thing of deep learning, because if you want to get better, you don't have to invent great new algorithms or something like that. But normally, the easiest way to make your model better is to collect more data and increase the size of your model. And which works for some time, but of course, there are boundaries. And if you get bigger and bigger, there are several limitations which make it difficult. And one limitation is the calculation. We looked into that a bit, that you're building dedicated architectures. If you remember the state space models, for example, which try to make them more efficient for inference, or transformer, which was like very efficient for training them, you're porting them to GPUs, but today we want to look what effects does it have on training. Why is it so important? Is because we're just having these really large models. If you look, this is more like now on text-based models. BERT model was for some time the default thing. If you look, I think around 2018, 19, how many papers there were citing BERT and taking BERT and like working on that. It was like the default model. It was very huge at that time. So not like every university there could train one. You could download it and adapt it, but it was really huge at that point. If you compare it to what I wouldn't call it even now anymore, but if you were going to GPT-3 size, we're having many, many, many more parameters. And so this might be an issue. The first question is, what influence does it have on the architecture? So typically, the number of parameters is influenced by two things. So the one thing is you can increase your parameters by making your hidden representations bigger. So if you're going from 100 to 1000 hidden dimension, this will of course increase also your number of parameters. If you think about a normal linear layer, how is the increase in parameters? If you double the hidden size, roughly. Do you also double your number of parameters, or what would be your estimate? Yes?
The growth should be progressing.
Yes, so normally you have, if you think from one layer to another layer, you have the matrix, which is the number of parameters, because you take the matrix to get the next hidden representation. The matrix has always input times output dimension. So if this is now the same, so you always have the same hidden size, which it means is, so if you before in one layer, if you had a matrix 100 times 100, now we have 1000 times 1000. So you're increasing that number of parameters there by quadratic. The other way to increase your parameters is, of course, going deeper. So instead of having 5 layers, you can have 10 layers. What will make this from your parameters? Yes?
That will linearly extend.
Yes, so yeah, I mean, you just copy and have double as, if you have double as many layers, you have double as many parameters. So you're linear scaling there. But you're seeing, yeah, that in both cases, it's a very nice, easy way to increase your parameters and thereby your size of your model, and typically also your effectiveness. It's not really significant work to do to say, oh, not use 2 layers, but use 5 layers now. It's like maybe 1 line of code, depending, maybe 5 lines of code, but it's not super difficult. So it's a very easy way of making your model more and more powerful, but what effect does that have on training? There's several effects. One thing is that you, of course, might have stronger overfitting. So if you have now a model the model can learn, of course, more specific things, and it might not learn the general thing, but it might concentrate. It is powerful, so it can learn very specifics of your training data. So if you don't have enough training data, you might end up with heavily overfitting. So that means, okay, we have to maybe address this type of overfitting, and again, develop methods that prevent overfitting so that we can train also like large models on the resources we have. Because yeah, generally we see that there's more overfitting if we're increase the model capacity in that way. The other challenge is that we might end up with a bit like of unstable behavior. So that means that the training gets more difficult. If you have trained neural networks, you'll see that. I mean, yes, before you see here the very nice curve. This goes always down. But if you have trained any network before, you'll see that typically things are not as smooth and nice. You have like a more shaky behavior and things go up and down. And generally, if we're training them, things get more unstable. Might be that we have seen one problem with RNN already with the exploding or vanishing gradients. But in general, if of course you have a bigger model, this can also happen more. Because if you think about it, if you do the back propagation, if you change one weight, you're changing it in the direction to make your error lower. But the assumption is, of course, that all the other parameters will stay the same. Then you're only like, it's like the direction of that, given that all the other parameters are the same. If you change all of them in parallel, which you have to do because otherwise it's not efficient, the more you change in parallel, you also change other things, and maybe this direction is even the very wrong, and you're changing the wrong thing. So if we're updating all parameters in simultaneously as we're doing, it might that we are getting up into some type of unstable behavior, that we are changing things that not easily can recover. So you can assume it here. So if you're optimizing the parameters here, you're assuming that you get the output from the previous layer. If you're now, other way. So if you're changing them there, you're assuming that the input is staying the same. But now if you change also here in parallel, the input is already different. So you might have to have changed in a complete different direction. However, of course, it's not efficient to train each layer independently of each other. So first train the first layer, then the second. With small networks, you can do that. But if you now think of layers of networks with 100 or 1,000 layers, then things get very, very inefficient. So we have to check in how we can adapt these things. And that is exactly what we are planning to do today. We're trying to first, we'll have a look at overfitting. So we're trying to look at techniques that try to limit the number of the overfitting that we're doing. The techniques we want to look there is first regularization, where we a bit limit again the possibilities of our network so that it's somehow concentrating on learning the important things. Then we'll look maybe at the most common technique that is, I guess, always used at the moment, which is called dropout, where we learn always only a part of the network. And we'll look into label smoothing, where it's more at the loss function, and we're trying to address their summation. Then, as I said, we're having these problem of vanishing and exploding gradients, similar to what we had in RNNs. And there we're looking at two ways of addressing that. The one is normalization, where we try, that is motivated what we saw before, saying that, if the input changes completely, then what we should learn is very different. So by keeping things more stable, maybe it's easier to learn, and that you can do with batch norm or layer norm. And then we'll have the residual connections, which again gives you a bit of idea again from the RNN, where it always was the idea that the gradient flows fast. And so similar, we can do a similar idea here. Then we'll talk later about initialization and the mixture of experts, where it's a bit for large networks, how we can distribute the computation and maybe have a large model where we don't have to compute everything, but only like some part of that. Before we go into that, do you have any questions? Okay, let's start with the regularization. So the idea is, I mean, in neural networks, it's very easy to always have a lot of parameters, just add them. But maybe not all of them are very helpful. It would be like very difficult to by hand decide which ones are helpful or not. And thereby what we can instead do is, oh, maybe we can just optimize it in a way that it prefers solutions which uses less parameters. So can we optimize it in a way that we're saying, oh, this is the possibility of parameters you have, but please try to get as good, but with less parameters. Now, doing less parameters as a discrete decision, like should I like 7 or 5, is always a bit difficult. We know that optimizing discrete decision is difficult, so we can also try to make it more in a continuous way, saying that a parameter which has a high weight seems to be a bigger parameter. A parameter which is around 0 is not really that important. And so we're saying, okay, so let's try to make a network where the weights are generally as low as possible. How can we do that? Now, that's now the nice thing about neural networks. We can just add more things that should learn. So we can add things to our loss term and say, not only try to learn this, but try to learn additional things too. So what we can do is we're just adding a loss term here where we're optimizing our function in a way that on the one hand, it should of course still be very similar, the output to what we want, but there's a second term which should not only do that, but in addition, it should also find a function where somehow the parameters that we have here, tether, have a very low value. Exactly how this R looks like, we'll have a look in the next step. There's one challenge with that. Does anybody see that? When this typically, if we're not having like, if our loss function is decomposed of several terms, but not only one term. Yes?
One term could outscale the other.
Yes. So one term could be more important. And how do we try to address that in the formula here? Yes. Yeah, so we have an extra parameter saying, okay, how important each one. It's a bit like, okay, do you put more preference on being very good, or do you put more preferences on having a small network? And that, of course, is a bit of a challenge because it tells, I mean, now you have something else to decide. So how much effort do you put into each of them? And that might not be super easy always. Yes?
Why is the loss term not the most trivial form?
But not?
Why is the loss term for the regularization not the most trivial form?
Yeah, you could, I think, also do that, but I think I'm not exactly sure, but normally this is the more, I guess it's also more stable if you add things up. If you do multiplicative, things might get more unstable. But I have to admit that's more like a guess now. I just haven't seen it, if I remember correctly, that it's multiplicative. So this is a bit more the common thing people are doing. I would assume it's about stability, but I'm not super sure. But this of course comes with a cost. So now you have to decide on what is a good lambda. And of course it's a bit clear that you have to put some preferences before you can say, oh, it's easy, optimize it to be the best loss. Now you have two things to climb and you have to somehow decide which one you should prefer. And that might not be so easy because as mentioned before, this lambda also depends on like how big the scales are of these two. So it's if you're starting to do multi-objective optimization, you have to somehow do this decision on how much you put on each of them. Because of course you get different optimize on that, and yeah, it's making things more challenging. So beside that, of course, the question is how does your R look? So how do we measure what is a good model that uses as few parameters as possible? The one and the first thing, easiest thing is one regularization, which means you're just taking the absolute value of all your parameters. Which means on the one hand, this is of course also a very sharp function, which will end up that typically some features values really get zero, because it doesn't matter how high the value are, it always tries to remove or to decrease the one parameter where it's easiest to decrease without losing something on their performance. So it doesn't matter if this parameter is around 1 or around 2 or around 0.2. If reducing this one is less affecting your overall loss, it will reduce this one. And therefore everything will, or like some of the parameters which are not useful will end up at zero. Making, it typically more a feature selection thing, where in the end you really have someone which end up at zero. The other one is what is called the L2 regularization. In that case, what is happening is that, very high level values are even like leading to more loss in your, or to a higher contribution to this loss term. So the model will more prefer to decrease very high values, and once they are very, very small, the contribution to the loss term is very, very small, so they might not really change them to zero. So you have a more smooth function so that more and more values get around zero at the end, but doesn't need to be exactly zero. Yes?
Are these small values then set to zero during inference?
No, typically not. So that's even typically, even for L1 regularization, you calculate all values, and it's more about like it's typically less computation aware optimization, but more like from the learning perspective. That's maybe because of restrictions. Can anybody assume why that might be more important in current hardware?
You mentioned with the GPUs that we need the same size everywhere, and if we would remove the zero values, then we don't have the same size.
Yeah, so it would be, I mean, you have a sparse matrix, and sparse matrix calculation is not really more efficient than dense matrix calculation, at least in the default hardware. So that I think at least in default model, that is not done. There might be special cases where it's different, I agree, but in the default thing where you just optimize on a GPU, then you would more like try to do just keep them as zero. And like always, there's also the way of combining things. That's what is called elastic NAT, where you then just combine the L1 and the L2 norm. And now I forgot a square in there. So you mainly do in front here, you do the L2 norm, and then you have the L0 norm there optimized for something. Good. Any more questions? Yes?
If all parameters are just set into or around zero, what exactly is the advantage if we still calculate with all of them?
I mean, the idea is that you have somehow less overfitting, because you have many parameters. You can learn very specific things which might not generalize. By this one, you tell the parameters, oh, I only want to have you influence if you really can contribute something, if it's important to learning. If there is a minor change in the loss function, ignore these parameters and don't further optimize them. Good. Any other questions? Good. With this, we're then going to the next idea, which is called dropout. And the idea is even more simple. The idea is during training, randomly, we select some of our neurons in the neural network and set them to zero. So we're dropping them, we're ignoring them, and we're like reducing our main network by this network. These are not contributing to the network. And a common value is even taking half the network as dropout, so saying that half the neurons in each iterations are not contributing. So how does it work? So here's a very, very small network. You have 3 inputs, 2 outputs, and then you have here 2 layers. The lower layer has 4, and the upper layer has 2. And what we're now doing is we're randomly checking some and saying then to 0. So we have then, for example, this type of network. And if you now look, for example, K21 has no longer, K21 here has no longer input from 1, 1, 1, 2, 1, 3, and 1, 4, but only from 2 neurons. So it has to get these informations from these two. And the same thing is here. This one only gets input from these two and not from that. Or the output then gets only input from here and here, but not from this one. Since it's random, another situation could be something like that, where we're now dropping two things from there and one thing from this. What is the motivation behind that? So one way of viewing it is that we are trying to learn more redundant features, that because it has to be able to even recover things if they are different. It shouldn't learn things only in one, but it should really extract the important part of it several times and be redundant. Furthermore, it should prevent co-adaptation, that you cannot assume that some other unit is also active and somehow use that, but you should have all the important information somehow stored there. Another way of viewing it is that we can assume that we're in parallel training a lot of models, smaller models in parallel. So another view is that we're training an ensemble of models. So you can assume that each mask is a model. So every time you mask different, you have a different model. So what you're now doing is you're training all these models in parallel, depending on which nodes you're currently removing. And of course, they are sharing a lot of parameters, so they're not independent. But you're always training a different model, and then later you're combining all these models again to make a general decision on how good you are. That's again the idea. If you have a lot of models, it might be better to train different models and then combining them. So you're doing that here also. So if you think about that, if you have 4,000 parameters, that means 2 to the power of 4,000 models, which is like a huge number of different ones. And of course, that's only possible because you do parameter sharing. Not all the models are different. They share a lot of things. It's just that not always everything is active. So in training, this seems to be quite straightforward. I mean, when you're training, you just, once you calculate a layer, you're masking the outputs and generating that. So training is in that way straightforward, but things get challenging when we think about the test. So what now happens is somehow that our output is random because it depends, our function not only depends on the input and the parameters, but also on our random mask M. So if you mask other units, you'll get different results. And I mean, in training, that doesn't matter that much. You're training, you're comparing, maybe you get a bit of a different loss term every time. It's typically even more robust. That's why it's working good. But if you have a network, that's typically not what you want to have. You want to have for the same input, you want to have the same output. Now it depends on your masking. So the question is, what can we do to get some of the same output to the same input? Any ideas what to do? Yes?
You could run with multiple masks and with the average or something like that.
That's exactly what we're mainly doing. And the nice thing is we're not even having that we're now looking at. We don't have to run it multiple times. If we are looking at the mass, we can make it in an intelligent way that we can do the average without running it multiple times. So the idea is we want to average out the randomness, as you said. So what we mainly want to do is like your output should be the expectation of this function with respect to to the masking, or if you are going back to very long mask, that is like you're taking the integral of the probability of the mask times the output with this mask, and that you like do the integral, or the, if it's discrete in this case, over all possible maskings. So what you're really doing is you're summing over all possible maskings, then you're multiplying the probability of this mask with the output. Which probability should we assign to a mask? Any good guess? Because that we need now, so that might be a bit. Is it challenging, or do you have a good suggestion? What probability would you assign to a given masking? Yes?
But they are fully random masks, and each mask should have the same probability.
Exactly, and that's what we're doing. And then we're getting to a very nice solution. So let's start with a very simple example. So you have a single neuron which has two inputs. So what this is here, so you have two inputs, then you calculate the weighted sum here, that's A, then you do your activation function, and that's your result. So, and the single neuron has two inputs, then it's like parameter 1 times input 1 plus parameter 2 times input 2. That's like exactly how we do the weighted sum, the most simple one. And we want to calculate now the expectation value and the possible mask. That's why we do the minimal one. Here it's still somehow possible, so there are 4 possible masks. We can mask nothing, we can mask everything, or we can mask one of each. So 0, 0, 1, 0, 0, 1, and 1, 1. And then let's calculate what is the results of the weighted sum. And the result, so the result is 1/4 times, when both are not masked, plus 1/4 times the one is masked, times 1/4 while the other is masked, plus 1/5, both are masked. And now you see that each of the H1 terms are occurring exactly 2 times here. So it's 1/2 times the first one, and 1 plus 1/2 times the other one. So this seems to be now very easy. So in order to calculate our output, what we just have to take is we're taking the output we calculated without masking and multiply it with our dropout probability. That's because everything is linear, so things are easy. And so at test time, what we just have to do is the output of the weighted sum, what we're doing is we're multiplying it with our output probability. And then we have exactly achieved that. It's also a bit like, if you're more now, go away from the math, you just think logical about it. So if you have a neuron, you get sometimes the input, sometimes you're not getting the output with probability 0.2. To get what you're in average you get, it's maybe good to just take the output and multiply it with 0.5 to do that. So how these networks look like then is that you put it typically here, you put in what is called a dropout layer. And this is behaving differently in training and testing. So in training time, you're applying their random dropouts. So randomly you set these values to 0. And at test time, you're multiplying them with the probability P. So you're in training, you randomly set them to zero based on the probability P. And then at test time, you're scaling it with P. And this is, mainly everything you do with a dropout layer. There's no only one. A disadvantage is, of course, there's additional calculation, and especially in both cases. So in training, you have to randomly drop things, and in testing, you have to always multiply with P. Especially if you now think about applying neural networks. You train them once, but then you apply them a lot of times. So the question is it also possible that we don't have the extra calculation during testing? Anybody have an idea? Yes?
You could just multiply the weights.
Yes, that is also possible. There's even, yes, but I agree that I think it's even mainly the same thing with.
I think the problem with that idea would be, another thing about it, the activation functions, because they depend on the magnitude of the output, right? And there could be constant weights. So you would have to multiply the activation functions too.
I think it's because you do that, maybe it's even possible. Just typically implemented it the other way because it's not, I mean, you have a specific dropout layer, and so it's not directly connected to the weights. So what you're doing is you're just multiplying by 1 divided by p during inference, because then everything is 1 divided by p larger. And then during test time, you would have to multiply it with p times 1 divided by p, which is 1, which means we have to do nothing. But that's more like an implementation detail. Thing with your thing is that's working easily if you have a feed-forward network, but you can have a dropout network anywhere between it easily, and then things might get more complicated. So typically you have this type of dropout layer there, which will just drop out things and do exactly this. And with this type of implementation now, where you do the scaling and training, you even have to do nothing in testing. So in testing, this layer can just be ignored. Good. Any more questions? And then we can go to the last technique, which is label smoothing. And this is more for multi-class classification. What you hopefully remember is that, we have our softmax activation function here, which gives us like the softmax function over everything, and then we compare to our reference, and now and then we're multiplying the output to the correct solution given the distribution, where the distribution is here more smooth distribution, and the reference we have is like a sparse one where there's 1 is 1 and all the others are 0. And that has a problem. There is now a difference between our reference distribution and the one we're learning. So the reference distribution is a sparse one, where like there's 1, 1, and everything else is 0, while the one we're learning is typically a smooth distribution by this one if we're not having infinity in there. And so then things are not that easy to learn. So what typically then might happen is that when we have very long training, that parameters gets very large in order to like really optimize the solution and get very, very sparse. And maybe we don't want even that sparse distribution, because typically we might have at the current position, there's only one possibility. But if you think about a lot of difficult problems where you use neural networks, that's even not correct. So if you're training to predict a sentence, yes, it tells you the next word should be KIT, but maybe Karlsruhe Institute for Technology as 3 words would be also good. It's just that in your training data, you have only one label. Or in vision, it might be also that, that wants you to do exactly this image, but maybe a very similar image would be also fine. So your reference is only like one solution, but in reality, that is one good solution, but not all the others are really bad. And but what you're trying to learn here is really that only this one solution is really good. So therefore, it has been shown in some tasks to be helpful that we're also trying to get a more smooth distribution in as a reference. So that we're not trying all our parameters to have exactly this one distribution where only one word is correct here, but more smooth distribution where this is the best one. But if some mass is distributed to other words, that's not really super bad. So how can we do that? It's quite straightforward. We're starting with our reference distribution. And if you want to do a smooth distribution, the first thing you typically have to do is you have to remove some probability mass from the correct solution, because you still want to have a probability distribution. So the first thing is you remove some probability mass from here. And now you have additional probability mass, which you can distribute. And now, of course, there is a lot of ways of how you can distribute your probability mass to other things. The most easy one is always to take the uniform distribution, just saying that you distribute your epsilon across all the others with equal distribution. Now you're not having a very sparse distribution anymore, but like a general, more smooth distribution. And you hopefully will not now try to learn to really get the best. If the correct solution is one and your model predicts this was 95%, that is fine. You don't have to go now for 99. You should better use your parameters to learn something else in there. How you can do that is now from the implementation side of view. There is different ways of how you can learn this type of distribution. So on the one hand, you can implement that on your reference, on your labels, saying that, yeah, although my data says it's this word, in reality, I want to have this type of distribution. And then you give this distribution as your reference. The other implementation is that you change your loss function so that the loss function is not calculating the loss between the reference and your distribution, but first changes the reference, and then it's more like a minor detail, but this is how you can do this type of implementation. So in total, we have seen now like 3 different ways of how we can try to adapt or like address the challenge of overfitting. We looked at regularization, at dropout, and now at label smoothing. And if there's questions, yes.
But do we actually get the probability distribution anyways and say, okay, this word has the highest probability and take that?
What do you mean?
I thought normally we get a distribution.
Yes.
The system says, okay, this word has the highest distribution.
Yeah.
So this is the most probable, the word with the highest probability. So why do we take this word and change the probability of all the other words?
This is not for the output probability, but we are comparing the network output probability to a reference. And the reference is typically saying, oh, it should be the word X, Y, Z. And that is now, if you think it should be the word X, Y, Z, that is sparse distribution because it says only this word is correct and all the others are wrong. And that's what we're trying to do. We're saying, no, this is correct and all the others is wrong. We're saying, oh, this is the most important, the best one, but all the others are not so good. That's like the extreme case of it. Yeah? But yeah, I think a very, very important point that we're trying to do. Good. And with that, we would then go to the next part where we look into the training and where we more try to look at the gradient, try to normalize them or look that they're not getting too big or too small or something like that. And the first idea is, as I said, if we're now thinking about deeper and deeper and deeper networks, if we're changing, if we're doing less changes to the upper layers, because the lower layers are the input to the upper layers, if we're changing the lower layers very, very strongly, that will affect the upper layers and they have to learn something completely different. And then we, of course, we want to keep being stable. And therefore, the idea is that we somehow keep the distribution of the hidden activations of a layer stable. So for like one neuron, I mean, maybe it's sometimes 1 and sometimes 0, or it's like can also have all the variables between that. But you are now what you're now trying to do is, okay, it shouldn't be at the beginning always 0. And then if you train at some point, if it's then always 1, then of course the upper layers get a very different signal. And what they've learned before, that this is always 0, is no longer true, it's always 1. And then what you learned about that is no longer helpful. And therefore it might be good if things are staying somehow more stable. So that this neuron is sometimes 1 and sometimes 0, and that stays all the time the same. How we're doing that is by normalizing them. So we're just forcing that this one has, over the training examples, has a Gaussian distribution, which you can do by saying, oh, we're changing the activation of this neuron by taking the original activation, subtracting the expectation value, and dividing it by the variance. Then it will have an expectation value of 0 and a variance of 1. And so it somehow behaves always the same. Of course, depending on the input, it's still different, but we're ensuring that it's not from a neuron which is always 1 changing to a neuron which is always 0, and therefore we have to learn something completely different. So yeah, the idea is to make things more stable in that way. If we want to do that, so if we want to normalize this and like stay keeping the information that we get from it more stable, of course, what we have to do is now somehow estimate our expectation value and variance. And how to do that in batch norm is, again, we would have to do some type of approximation. Why do we have to do that? I mean, if you do that now, if you run over all your training examples to calculate it correctly, you have to run over all your training examples, calculate the expectation value, and the variance, and then you can normalize it, which would be very inefficient. So before updating things, you have to first calculate the variance and the expectation of all training examples, which is inefficient. So we have to do some other trick and approximate the expectation value and the variance, because if we would have to calculate that exactly, things would be too slow. Any idea how we can approximate that instead of going over all training examples?
Now maybe use a smaller subset of data.
Yes. What is a good, if you look at the name, what is a good subset which we could take? Exactly, and that's what we're doing. So the batch we're any calculating in parallel, so there's no extra calculation in doing that. So instead of calculating the expectation value and the variance on the whole training data, we're calculating it only on the current batch, and that we can do quite fast. So how to understand that? So what we're having is typically like X is our n-dimensional vector. That is our hidden state at one layer or so. That's the n-dimensional vector. Now what we have is we are calculating it in parallel. So we have a batch with size big B. So in total, we have this type of matrix where here as a row, we have one hidden state and the next one is another hidden state. And then one column is, for example, the last one is the last neuron in this layer all. If we now want to calculate the batch norm, the expectation, what we're doing is we're calculating it in this column. So if we're taking the last one, if we're summing them up and squaring them, just summing them up, that's the expectation value. So that's the average value we have in the current batch. And then similar, we can calculate the variance with the formula of the variance. So we're doing that for all the different neurons in our layer. We can calculate in the current batch, that is the expectation value for the first neuron, for the last one, the second last, the third last, and so on. Yes?
So this happens after the original calculation of the XI.
Yeah, so you first calculate the XI, and then you can calculate that's a good point. So you're first calculating XA, then you're calculating the expectation and the variance, then you can normalize, and then you can continue. So you have a batch norm layer, mainly before the activation even, that you're not further calculating with the current value, but you're further going with the value that is normal. So what you can now do is, like always for the weighted SEM, you can do this type of batch norm, do the calculation, and then continue with this normalized. With the good thing that then things are normalized and they're always between they're always centered around 0 and have a variance of 1. And then you add these types of layers in there in Duke. Do you see also any challenge that could happen with that? So is it now everything good, or yeah?
Mean and variance for inference as well. And there we only have one sample.
Yes, exactly. So that is one challenge. We'll come to that later, but even during training or like more for the model, So that's a good point. We'll come to that later. Before that, I want to do one other thing. You see also here?
The multiplication of the xi strong depends on the input. So depending on if you have very different inputs, the scaling could be very different, and that could, in a sense, confuse the network.
Yes, there is one way of trying to address that, and that's also like a bit of a disadvantage of batch norm. How can you try to prevent that? That once you might have very low values and once you have very large values. When is your approximation getting better? What can you change to make the approximation of the overall expectation value better?
We can make the batch size larger.
Exactly. So the larger your batch size, the better your expectation is. Hopefully, then this will also change. So that tells us, okay, we need large batch size, but it might is an issue because maybe we can't have that large batch size. Also, the other problem is that you might limit the neural network by having a fixed mean and variance. So it can, or each neuron has now a fixed mean and a fixed variance. It can't learn nothing else, which limits some of the power of that. So what you do is here, you put, as I said, the batch neuron now after each P4 network, for example. So you have P4, then you have your batch neuron, then you have your activation, and so on. So you can integrate your batch neuron layer there all the time. We saw how to calculate that, but we might have now a more limited network because it cannot learn that, oh, in this case, it should be always very high because they all have to be like somehow between 0 and they're normalized to 0. Any idea how we could address that? It might not be the best to have everything fixed with a fixed mean and variance. What we can do, we're just learning that again as additional parameters. What should be the mean and the variance that we want to learn? So we are first normalizing it. No, first calculating expectation variance. Then we are normalizing it. And then we have two additional parameters. Gamma? No, I don't know. And beta, which now scales it again so that we have any variance and shift. So expectation that we want to have. The advantage of that is that we're learning that now explicitly, and we're changing that explicitly, and it will be constant over different samples. So it's not that we're like randomly have that. Well, we can explicitly learn how we do that. So what we're doing is that's why we're implementing it now in these 3 steps. That we first do the calculate the expectation and the variance, then we do step 2 where we normalize things, and then we do step 3 where we're rescaling them. So we can still have the full power of it, but it's not that this is changing very, very frequent in there. So the advantage is that it typically improves the gradient flow, that we can thereby then have higher learning rates because we can do larger changes. Also, it less depends on the initialization and gives us some type of regularization also. Yes?
Is that third step rescaling needed in a fully connected layer? Couldn't we learn it in the weight matrix of the next layer? If we have a bias and a weight for each layer?
Yeah, but this is done before the activation, the non-linearity in the and the test time, you mentioned it, there might be a problem, but what you normally do is you're calculating the average over your training, and then you're taking some mean and mean values for the mean and the variance from training and keeping them fixed and applying them always in testing. Because there you can use the ones from the previous because the weights no longer changing. In training, you can't like just keep them fixed because the weights are changing, but once you fix there, you can keep some fixed values there and continue using them. How that helps was shown here for some vision network where we have again the loss and or the accuracy and the thing. The interesting thing is the red one, which is the baseline, and then you have the batch-norm one where you see that you're on the one hand you're learning faster and you're even getting mainly, I don't know if it's really much better performance, but you're getting here, I think this one, the green points are all the same. So you're very much earlier getting the same performance as you get with the other models later. So it was match norm, you're faster trying to get the it has, of course, also some disadvantages. The disadvantages are, on the one hand, that you need a large batch size. That's what we said before, because in order to calculate that efficiently, you need to, not efficiently, but in order to calculate the variance in a good estimation, you need a large batch size, which also means large memory footprint. It also means you can't easily do the mini batching where you just do several in parallel, because you have to calculate all the examples of that layer before you go to the next, because you have to do that in this calculation. Here, you're in the BN calculation, you need the variance of everything. So you can't do like first 3 examples, everything, and then 3 other examples. You really have to, if your batch size is 6, you have to do the first layer for all 6. Then you can calculate the normalization and go on. So just splitting up your examples and doing them independently, as you can do for gradient descent, doesn't work here easily. Furthermore, it of course doesn't, I mean, it works on the top. If you have this now, the network rolled out for a longer sequence, it works on the up-down axis, but there is nothing happened in this one, in the XYZ. So you might still have a lot of variance there for different inputs. And that's why people also look into what is called a layer norm, where you do the same thing, but now you do the normalization across the feature dimension, meaning you're taking the expectations values now here for one hidden state and normaling them to be between 0 and 1. The nice thing is that you can do, for example, also for all time steps in the RNN. But the disadvantage is that this typically is not as efficient as the batch norm, where you do. Still, both is happening, layer norm and batch norm. Good. Any more questions? Then we'll come to the next point, which is residual connections. And for that, recall what we once did for RNNs. We said, yeah, if you apply the same type of update all the times, like in the large neural network, if you remember, we do 65 times, then if this WH is a bit higher than 1, you get very low value. And if it's a bit higher than 1, you also get it really bad. Meaning that, yeah, if you backpropagate from left to right here all the time, this is not really efficient. In order to do, like, get the feedback, sorry, to here, that's very difficult. And that was about long sequence lengths. Now we get a similar problem with large networks when we are going for very deep networks. So here on top, we get our loss function. It's like typically the loss term we get on the very top at the output. And now we have to backpropagate this loss from up there down all the way to our inputs. And we have to always multiply with the derivation at all layers, and that might get difficult if they are too low or too high. You might get very low derivation as learning is getting problematic. So we always need to back propagate through all the layers all the way, and that is making things challenging. And we had this already mentioned shortly in the transformer layer. Does anybody remember? There, this was addressed. So we had already these connections around the transformer blocks, which we call residual layers, residual connections there, but we didn't explain them in detail. And that's what we want to do here. So what it mainly means is we are calculating now our hidden function a bit different. So typically our hidden function was f of x, where f could be a feed-forward network or RNN or self-attention or anything. So our hidden representation is always we take a function from our input. So if you have a feed-forward, it's like matrix multiplication times this. And that is our normal one, and we visualize it like this. You take your x, you're putting it through a layer, and then you're getting your output. Now in a residual connection, you do something really, really simple. You're saying, oh, you're just adding to your input, to your output, you're adding also the input, and that's your final output. And that is all that is happening. So instead of predicting directly the output, we are more predicting what do we need to change on the input. So you can visualize it also different. Just assume this is a default route. So your input is also your output. And now what you need to learn is, oh, how do I need to change the input in order to get the output? So you only need to learn the delta. And in a lot of scenarios, it might be easier. Instead of directly learning or completely learning what I need to do, I just learn now what I need to change on the input to get the output. And that is what is done in residual connections, where we have them, and they can be even not only on single blocks, so you can even have them on several blocks, that you always only learn how to change things. From the derivation, you also see that. So normally your derivation with respect to the input is the derivation to the hidden function times the derivation of the f with respect to x1. And now here you see it's 1 plus that. Meaning also, like, if the derivation here is very low, very small, then since you multiply it, somehow it doesn't matter, you're just staying the same. Before you get a very small derivation, now it's just you continue giving the derivation. And if it's very large, maybe the difference between the very large value and the very large value plus 1 is not too big. But if you multiply with something, maybe it's better to multiply with something around 1 than to multiply something which might be also nearly 0. Of course, also from the motivation, it really works. So this is from the ResNet, so the original paper. It was defined. Sorry, it's a bit small. So the first thing here you have in this, can you see the greenish ugly line? So this is the 18-layer network, and the red one is the 32-layer network. And maybe the surprising thing in the first one, in the baseline system, is that at the end, the 18-layer network has a lower training loss than the 32-layer. And that clearly says something with the optimization is not working. Because with a bigger network, you can always approximate the smaller one. You can just learn that the lower layers do exactly the same, and the top layers just do nothing, just do it directly transport to nothing. So seeing that the small network, not on the test, but on the training, might generalize it, but on the test, it should be at least as good as a larger model, because it can always simulate the large model. However, in the normal training, you saw that this didn't happen. So even in testing, the model was worse. Because it wasn't able to find this type of simple solution. If you now look on the right thing, where there's ResNet, you see now the large model is better than the small model. So since you're doing this idea, the gradients flow somehow a bit better, and you're getting overall a better performance in GPU. Yes?
For every column, there are 2 lines per graph. What do they represent?
I think that the one, I have to check the paper, but I think the one is a test and the other one is a straight line. But you see that in the left one, both of them are up, and in the right one, both of them are lower. Good. Any more questions? Yes?
Where do you typically apply residual connections? If you do residual connections on most of the network, so let's say from the start to the very end, then you would have pretty bad results because you limit what the network can actually learn, and you force the network to keep an internal representation, exact representation of the input. If you do it too close to each other, then you're not having that much of an effect. So it's very kind of a rule where you.
I think I don't have it. Yeah, I mean, normally you really do it just around every network around, because then still, I mean, you have to apply because it just goes over everything. So normally you have a full connection. So normally you have residual connections like from bottom to top, but not going over it, but always going further away. So that there's a full connection through it, but it always only goes across one layer. Or, I mean, now the definition is what is one layer. You think about the transformer. I don't have the transformer image here, but you have a mixture. One layer consists of different sublayers, and they are of different types. And there, I think it's even typically that you go across each type. What you're not, if you now have a layer norm or something like that, that you combine maybe, and you're not doing like feed-forward activation and layer norm individually, but across all of them. But if you have in transformer, for example, you have first the self-attention and then feed-forward network, and you have a residual across both of them. So here you see how that typically works. You really like always go around that and then take the input again and go around it. What you can then also do is like you can combine it somehow with dropout in a way that what you're now doing is that a network is no longer learning a new representation, but it's learning some to learn what it should be changing. What is a good thing is now when you learn what you can changing, a solution of changing nothing is at least somehow reasonable. It's not completely wrong. Before, if you don't have a residual connection and you just do nothing, you have a zero input. Now, if you do nothing, what you have is the same as the input. So somehow just doing nothing is somehow more reasonable now. And that's what you can do, what is called stochastic depth. So you can combine that with dropout, where you no longer drop out now individual nodes, but in training, you can now also drop out complete layers, saying that, yeah, you're doing now, for example, the middle layer in some tested training in some layers, you're not training them, but just taking the input and taking as output. And that, of course, only works if you have residual connection. If you don't have a residual connection, the output would not be connected to anything before, or they might have learned something very different. Now, if you only learn to change things, the input, yeah, I mean, you have half your information or something like that by just copying things over. So you can do now what is called stochastical depth, where you like blank out complete layers and train them. There might be one advantage in training if you're doing that compared to the dropout we had before. Anybody see what is an advantage of dropping a whole layer instead of only like individual neurons?
Same on the computation, we don't have to compute it layer.
Yes, exactly. So you can really easily save a computation because you just don't do that at all for this type of layer. Good. Any more questions? Good. Then only 1 or 2 slides on initialization, very short. So if we're really using SGG for things we're supposed to work on convex problems, initialization doesn't matter because we always end up in our minimum. The problem is that initialization neural networks are non-convex, and therefore initialization is also quite important. And for example, the scale is important, that you're going in the right direction, like with the right learning rate at the beginning. So therefore, there is at least some rules of what is normally working well. So if you have a layer with m inputs and outputs, typically what you're doing is either the uniform or the severe distribution of them. So either only based on the inputs or based on the inputs and the outputs. And that is then the way how you initialize your weights. Because yeah, they should be somehow in a range that at the beginning you do a decent learning. If you think about your activation function, if the weights are very off, it's very hard to start the learning. It's very slow to go, and therefore, yeah, initializing your starting parameters is also from quite big importance for the further training of this type of models. Good. And then motivated by what we had just before, the stochastic depth, we want to extend it a bit more to what is called the mixture of experts, which is now a bit in between. You could also put it onto architecture. Maybe it fits there better, but yeah, since it's related to that, we'll come to that here, where we are now trying to, instead of drop a layer or not, we are looking that you might want to switch and use different layers there. The motivation is that, and the idea of this is already quite long, is that typically we have a combination of models is stronger than one single model. We've seen that today already with like this interpretation of dropout as a combination of models, also showing that it works better. And people have done that in ensembling. So often, if you want to build your best model, one technique is not to train one model, but to train 5 models and later combine them. The easiest way is to just, if it does a probability distribution, you just average over all the models you have. And often, even if the models are exactly the same, and no, they're not exact, but they're trained exactly the same, just for example, with different random initialization, they get already better. So the question, of course, can you do better? Can you directly train a combination of models? And this mixture of experts was already done before neural networks. First works in 91 on where you had like more rule-based experts doing specific things. And that is now what you also try to do in this mixture of expert models, where you try to now train, instead of expert systems, you try to expert components, which in our neural networks always means we're trying to somehow train some expert neural networks layers, and not all information will go through that, but depending on your current input, you decide where the information should go, and then you're not computing all of them, but you're like putting them only to some specific networks. You already hopefully can imagine that this might now be a bit challenging on architectures, and we're covering that only a bit. But of course, this dynamic allocating of components is something which doesn't directly fit on GPUs, because we said always, oh, we should do all the same calculation for that. How that is a bit addressed in mixture of expert models is now that you'll have, especially for models which are distributed over several GPUs, in the different GPUs, you'll have different experts, and then you try to distribute things to this type of expert. So how does I learn? So this is now from switch transformer. So one of the first networks where you try to do that inside a neural network. So you now here have again the transformer layer. So what you have here is self-attention. Then you have added norm. So that's mainly a layer norm, and then a residual connection layer in here. Then you have your mixture expert layer, and then you have the add norm. What does it replace? What in the transformer layer? What was here before? Anybody remember? We had a similar picture. It's some weeks ago, I admit. So normally that is where there's a normal feed-forward layer. So normally we have the self-attention, then the residual connection, and then you have here just the feed-forward layer. And now the idea is instead of having the feed-forward layer here, what we have is we have different feed-forward layers. Here you see 1, 2, 3, and 4. So you have 4 different feed-forward layers. And now, depending on the router, which is like a gate that will decide you should go maybe in the first, if you have a sequence, in the first step of the sequence, you go to network 2, and in the second one, you go to network 1. So you have a number of experts. So in this case, you have 4 experts, 1, 2, 3, 4, which each network is just, in our case, a feed-forward neural network. So it's just you have 4 neural networks in parallel, but now the difference is we're not stacking them, we're putting them in parallel, and then we have a gating mechanism to decide which ones we choose. So mainly for computation, it's the same as having 1, but we have now our gate network or router, which decide which network we can use. And we can even go further. We can also say, oh, it's not going through 1. We can also say it always goes to 2 or something like that. And that typically depends a bit on our current hidden state, so it should be. So to formalize it, what we're having is we're having an experts here, so which are in layers E. Then we have a gating network G based on our input. And that gives us an n-dimensional vector here saying how we should go to each expert. Can be that this is a discrete one, that only like one value is 1 and all the others are 0. It can be that it's a probability distribution or anything. And then our final result is it says how much weight we should put into the expert, the gating network times the output of the expert. This is our routing or gating. It goes to the different networks, and we're multiplying the output of the network with the gating. And that can be, as I said, discrete, so 1 and 0. It can be a probability distribution or anything. If it's, of course, a probability distribution, then the idea of routing is no longer be there because we have to go to all of them. If it's a smooth distribution, if it's more a sparse distribution, we're only going to some gates there. Yes.
How do you prevent the gating mechanism of always choosing the same neural networks? Because the other ones haven't been trained because they were never chosen.
I mean, you hopefully prevent that a bit by random initialization. So because at the beginning, all of them are somehow used, and then you're doing that. But that is a major problem. We're coming to them later. And what you can, of course, anybody has an idea? We had some of this idea today already, a similar one. How can we make sure that all our experts are somehow used?
Drop out. So we just drop out some experts so that the network has to take the others.
Yes, that wasn't the idea I had, but I at the moment see no disadvantage of that. So yeah, and in somewhere you'll do that. So yeah, that's also a good solution. There's one other I wanted to point it, but yeah, that's a good solution. Dropout was one idea to do regularization. What was the other way of doing it? Today. We had before the regularization loss, where we have another loss term. Exactly here, you can have another loss term telling us, if you're doing how much you use the different experts, and you want to have a somehow smooth distribution that all of them are used, and if one expert gets used too many times, you have that as an additional loss in there. So, okay, let's have a look at how to do G of X. So the routing. So the baseline could be somehow you learn a softmax where we multiply our input X with some weight matrix, and we get a probability distribution, and then we multiply this probability distribution with the output. Now, when making the slides, I didn't know that you come up with a problem already before. So, of course, the disadvantage is then that we need to do all experts in parallel. So, therefore, this might not be the best way of doing it. And instead, there's other things to do. One typical way of doing it is the so-called noisy top K gating, where the idea is, yes, we're doing our HK as before, as the xk times wg, that is as we had before. And now we are also adding there some more noise so that it's not always the same, so some random noise. And then we're not selecting all elements, but we only want to select the top k elements. So if the value is in the top k, we're using it. Otherwise, we're saying setting the value to minus infinity. Why minus infinity? If we are setting it to minus infinity, the softmax will be 0 here. And we're doing the softmax afterwards so that we now have a new probability distribution where only for the k values we have a probability distribution and all the others are 0. So that way we're now achieving that we're not having really a probability distribution over everything, but we have only over k values the probability distribution. Why might it be good to do the noise in there? And not just take without the noise? Yes?
So that the ones that aren't organically chosen also get chosen sometimes?
Exactly. So you want, I mean, especially if you do learning, if it wants to choose only the 3, it might always choose always the 3. And with the noise, you know, since you're doing a bit of a discrete choice, you're randomly sometimes switching to another one. So that it's not always taking this one, but sometimes randomly also some other ones. And then there is the load balancing, as mentioned before. So it might be that that typically it happens that some by random some experts get trained more, and then you mainly apply them, and that's somehow not the thing what we want to do. We're not wanting to really only use some experts. You want to use all your different types of experts. And that's why then, as we said before, in order to do some type of load balancing, you try to have an additional loss where you say that similar number of examples should be put by each expert, and you're not having only like 1 or 2 experts which are mainly used. Okay, before we are going to some examples, then maybe the last thing is so how you typically can do that is in GPU. So there we said this type of branching is difficult. So what you then try to do is, or what is often done is, that you're running your training on several GPUs, and you see that all the other layers are shared, and only the expert layers, they are distributed across all the GPUs, and then you're distributing your data so that on GPU 1, all the data points which should be calculated by the mixture of by the expert 1 are calculated, and GPU n, the ones which are calculated based on expert k. So then the nice thing is now you have a large network, but since this is shared, like during training, you only have to do like somehow 1 expert on every GPU, and therefore can do things efficient. There is one challenge here now, maybe. Can you see what could be difficult in that? We had it already mentioned a bit before, but now it's getting really difficult, not only computation-wise, but also computation-wise. I mean, the load balancing somehow gets even more important now, because now this GPU is doing everything for expert 1. Expert 1 has now too many, then this one will be slow. And if this expert has very few, then he'll have nothing to do. So you get very inefficient. Not only the learning, the performance might be bad, also the training is bad if it's not well distributed according to the different things. Yeah, so one or two examples. The one is the so-called G-share, where you have the scaling what we saw before. So the network here you see again the typical example of your of a transformer. So this is a normal transformer. So how that is here now doing is that you're doing the mixture of experts, and that is distributed overall. The routing is done that so they are only gated. So you have two experts for everything, and the first one is the one which it selects as the most important one. The second one is sampled according to the probability to have a bit more smooth one, so that you're not always taking the same two, but by sampling you're somehow doing that. And then there's also the problem with the expert capacity, so that this expert one can only do X, and if there are too many samples, it might not work anymore. And in order to handle that, we can now go back to what we thought about the stochastic depths, that if we don't do anything, that's somehow also working because we have the residual connections. So because of the residual connection, it also do fine to just don't calculate it at all. So what we can do then, if there's too many examples, then we just use the residual connections and ignore it there. Another example was the switch transformer, where you have only a single expert, and there you're also trying to calculate the capacity. And quite surprisingly, it really can work out with a quite low capacity. I mean, if you have 1.25, meaning it's like only 25% more or less you can have in there, it cannot go more than 20% over the expectation value in there. Good. And this summarizes today's lecture. What we did is looked at different techniques in order to make learning more efficient in very deep networks. We looked into regularization, dropout, label smoothing, batch and layer norm, residual connections, and mixture of experts. And before we finish, do you have any more questions? Yes.
So the experts are loaded in the sequence, all of them. Does it in some cases make sense to load some expert multiple times? Because then you wouldn't have the problem with expert capacity. You may not want to.
Yeah, but you don't know which one to load many times, and you want them to be from learning to have them equal distribution a bit. And I mean, if you would load one twice, in order to be fair, you have to then another one load 0 times, or like 1 time, and then you would say, oh, this expert is more important. And I think that's what you normally don't want to say. That's why I assume you always have similar capacity for all of them. Good. Then thanks a lot, and see you again on Thursday.